Hello, so today we're going to talk about topic 8 on reducibility. Last time on topic 7 on um, decidability, we've been talking about some languages that are decidable, right? Pretty much anything that is below the Turing machine, so that has to do with finite automaton and PDA and LBA um, is decidable. And there are some languages that are decidable and not in these categories. So we've seen some examples of decidable languages and also one example of undecidable language called ATM. So if you remember, ATM is the language of an encoding of a Turing machine M, string W. M is a Turing machine that accepts W. Okay, and we saw that ATM cannot be is not decidable, which means that um, it is Turing recognizable, but it is not decidable, right? So ATM is Turing recognizable, but not decidable. So it belongs, right, in our hierarchy. So all decidable languages are Turing recognizable, but ATM is in this in between, right? So we've pushed a little bit far the limits of computable languages to a point where we reach really the outer sphere of what is computable, right? So ATM is still recognizable by a Turing machine, right? So that means I can design a Turing machine that basically simulates, and it's really going to be what we call a universal Turing machine that simulates any encoded Turing machine along with its input. There's no problem. I can design it. It's going to work. It's going to turn. It's going to go forward into doing what the Turing machine does. But there is no way to make sure that it will reach a halt, which is what decidability is, right? That means that at some point it accepts or rejects the input. Um, and we saw formally why it is so. So you can look back at topic 7 if you want to look at that. It has to do with diagonalization, and basically it has to do with feeding the Turing machine to itself, feeding itself to the Turing machine, and designing a little contradiction. And at some point, there is no. We show that if we assume that ATM is a decider, then we reach a contradiction. So somehow ATM accepts when it rejects and rejects when it accepts. I mean, not ATM, but another Turing machine. So anyway, and we use for that actually the notion of reducibility, because we use that if ATM is a decider, we can find another Turing machine that has to be also a decider because it's reduced to ATM, and this other Turing machine is leading to the contradiction. So reducibility is going to be very important because ATM, in some sense, is really the archetype of the undecidable problem, right? It is ATM is not just a language. It is, if you want, a representative instance of the class of undecidable languages. And And then because it's a representative of this class, and it has the special like archetype status in some sense, it is going to be our lighthouse or landmark, if you want, to find a whole range of other undecidable problems. It is not the only one, but it is related to all other undecidable problems. It is somehow connected to all others. So this is how reducibility works. Just another reminder from last time, the last chapter on the decidability. We've really pushed so far to the limit of computation that we actually found some languages that are outside of Turing recognition. And an example of these ones is the complement of ATM. And we've shown that the complement of ATM can not even be Turing recognizable. That means that for this language, there is not even a Turing machine that can actually recognize it. It seems pretty esoteric to think that there are languages that cannot even be computed by Turing machines. Even when I say cannot be computed, it's not anymore a question of is it going to give me an answer? Is that the question is, can you even design a Turing machine that provide? And here you can't. You can't even design it. And the proof has to do with well, the proof has to do with the fact that it has to do with decidability, right? So even if you're at the outer reach here, it really has to do with decidability. And let's take an example of in the book of decidable problems, say a DFA, for instance, is decidable. There is a theorem that says if a problem if a language, it is actually the very last theorem of chapter 2, and I invite you to look at it. It's really powerful. It's 4.22. L is decidable if and only if it is Turing recognizable and co-Turing recognizable. What does it mean? It means that if ADFA is decidable, then its complement has to be at least Turing recognizable. It's probably also decidable, but we don't want to go in that direction right now. But we know that it's going to be here. It's not going to be outside, right? So if a language is decidable, you can design a Turing machine for the language and for its complement. It has something to do with to be decidable. That means that you need to be able to design a machine that says when it accepts and rejects and it will stop, then the complement, you can at least design a machine that will accept or reject for the opposite, or might loop forever. But you know you can design a machine. If a language is not even decidable, if it's not decidable, that means that by this theorem, its complement cannot be recognizable. And you can look at the proof. It's actually not that complicated to grasp. Okay, that was the last chapter. Now, reducibility is going to be very powerful because, again, it's going to allow us to define a whole class of languages by mapping reductions. So the chapter 5 in the book ends with mapping reduction and the definition of mapping reducible, I would start with that because on page 235, it's the definition 520, because I think it's really helpful to understand all that. So we say that language A is, and we write it like that, mapping reducible to a language B if there is a computational function f where for all w belongs to A, any string in A, there is, you can compute f of w that belongs in B. So, and f is really the, per se, the reduction from A to B. So really, that's what we've been doing many times in the examples of to prove decidability, and in all the examples at the beginning of chapter 5, that's always the same scenario. We define a certain reduction from A, and in many cases here that we have, it's ATM, to another problem. That means that we show that we can express this other problem, we can express the problem of ATM in terms of this other problem. So the example they give in the book is, if I'm lost in a city, I want to go to the theater, I don't know where it is, that's my problem. Well, I can find a map, which is another problem, right? I can go look for a map, and solving that problem will solve the first problem, right? So the problem of finding the theater is reducible to the problem of finding a map, right? So you can focus only on finding a map, forget about the theater, but when you're doing that, you're actually contributing to solving the other problem, and solving one solves the other. Okay, so that's really the basic idea of the reduction. The idea is that you can really build a Turing machine by defining it in terms of another Turing machine. Okay, for instance, another example could be to say that the problem of multiplication is reducible to the problem of addition. So if you want to multiply two numbers, but you don't know how to do that, if you build a machine that can do addition, you can repeat operations on this machine. So if you have a Turing machine that can do addition, you can therefore have a Turing machine that does multiplication, right? So solving addition solve multiplication. So the Turing machine that is capable of multiplication is reducible to a Turing machine that is capable of addition, right? So when we say that, it's very important, because that means that if one language belongs to a certain category, like cross a certain border, say the border of decidability or recognizability, and here we're talking about categorical border, right? So in some sense, we're not talking about anymore about regular languages or irregular languages, or context-free, context-sensitive. It's much more of a qualitative step here, right? Because it talks decidability and recognizability. This qualificative, this characterization talk about the very capacity of the machine, what it can do and cannot do. It talks about the limits of the machine. So regarding this limit, if you can prove that the reduction is very important, because if you can prove that ATM, another problem is a reduction from ATM, and here we have many examples. Let's try to. The halting problem, for instance, is the most famous one. It's actually halt TM. So that's the Turing machine halts. Well, because ATM can be there's a can be is mapping reducible to halt TM. Therefore, because ATM is undecidable, then halt TM is also undecidable, right? So it puts it in the same category. You can do the same thing with all kind of problems. There is empty language for a Turing machine, and there is the question of does the Turing machine recognize the regular language? All of these problems are undecidable because ATM is undecidable, and they are reducible from ATM, right? So in some sense, ATM is at the edges of undecidability, right? So it's, so you have, decidable and undecidable, or here it's going to be Turing recognizable, but not undecidable in this specific in between. So you really have ATM kind of at the edges, and then a whole like tree of other problems that are mapping reducible from ATM. So and some problems are actually also children of, I would say, grandchildren of ATM, in the sense that, for instance, the problem of the equivalence of Turing machine can be also shown to be a mapping reduction from ETM. Okay, so you can have here a whole like chain of problems that are all reduction of reduction from ATM. But ATM is really the anchor, right? And the post-correspondence problem that is not a Turing machine problem per se. I mean, it's not a language that contains encoded Turing machine, right? Unlike all of these others, it's a problem that you could say belong to another category, right? It's some dominoes that can be put together. Well, still, even this problem is shown to be undecidable because you can find a mapping reduction from ATM to the post-correspondence problem. And the way it works, you should look at the proof. It's a bit long, but it's really not that complicated and really interesting. It's just because of this, they are dominoes, right? Where you have some kind of string on top and string on bottom, and the question is that with all these dominoes, YZ, XYZ, can I find a way to combine them such a way that the string on top is going to be in the end completely equal to the string on bottom? Well, it doesn't really matter that sometimes there are only one letter here, two letters here. The number can be very different on top and bottom, so you can use that to say, well, the bottom is going to take one step ahead in terms of defining what is the current state of the machine, and the top is going to be my transition function, if you want. It's going to take the current state to connect it. So you're going to have the current state is going to be here. The state current state is here, and you have very it's a very, and you have here the next domino, right? Because the domino don't have to be, sorry, the dominoes don't have to be, you can have a diagonal like that, right? Because you can really add you can have A, B, C, and B, C, D, and here D, E, F. There's no problem, right? You can see how the this is going to work. E, F, G, and just G. These ones are going to work together as a line, because you're going to have A, B, C, D, E, F, G, A, B, C, D, E, F, G. But the correspondence is really going to be like this, right? So mine is kind of the other way around. But here my correspondence is like this. So that's basically to make it very basic, right? That's my transition function. I define transition function. And I just map the current state to the first part of the transition function, the state, the state and alphabet it takes into the value that it outputs, the function, right? So that's my transition. You can see it as my transition function. It takes, that's what it outputs, that's what it writes, basically that's what it reads, and that's what it writes. So you put this, you're gonna map the read to the current state, and you keep doing that, right? You keep doing that, you map the read, and so that's, you have the new current state, and then you map the read. And so basically, solving the post correspondence problem can be equivalent to simulating a Turing machine to see if M accepts W. So if you manage to define if you manage to define ATM as solving the post correspondence problem, you're done. Post correspondence problem cannot be decidable because ATM is undecidable. So A is mapping reducible to B means that from that you can get two things. If A is undecidable, then B is undecidable. But actually, it's actually the other way around. It's actually the other way around when you think about I'm lost in a city and I need a map. When you think about this problem, we're not talking about undecidable problem. We're talking about decidable problems. So actually, the more intuitive way of thinking of it, if A can be reduced to B and I can solve B, then I can solve A, right? So actually, the more intuitive result from that is to say, well, if B is decidable, then A is decidable. Right? That's very obvious, right? If I can reduce A to B, if I can reduce finding the theater to finding the map, then that means that if finding a map is doable, finding the theater is doable. That's what it means, right? That's the most direct result from it. The other result is that B decidable implies A decidable, right? Well, in logic, right? If you have A implies B, then not B implies A, right? It implies not A, sorry, right? So it's kind of really good to have always that in mind. This will save you in many situations. Always have this in mind, right? A implies B, then non-B implies not A. Well, so if B decidable implies A decidable, then A undecidable, right? If that is, so if when you have this implication, then that means that if this is not true, then this is not true, which is basically what we're saying here, right? So the reverse is also, the contrapositive is also true, right? So if A is undecidable, then B is undecidable. And when you think about it, it makes sense, right? If I want to find so finding the theater is reducible to finding a map. If finding a map is doable, then finding the theater is doable. If finding the theater is impossible, then finding a map is also impossible. It's kind of weird to think about that, but you have to think in terms of finding the theater is something that can be reduced to the problem of finding a map. Like, I find a map, therefore I find a theater. Right? That's what I said. If I find a map, I know I find a theater. That's true. Therefore, if I can prove that I will never, 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 ever find a theater, I can also prove that I will, based on what I just said, I will never find a map. Otherwise, my first proposition would not be true, right? Okay. So, okay. So that's really the reducibility in a nutshell. So how we draw that, like B decidable, A decidable, this is not as much explored in the book because it's interesting, but it's not as interesting. It's easier to prove that some problems are decidable. So we're not as interested in this kind of mapping thing, but it's still something important to know is that yes, if in some sense B is going to be on the other side, right? So if B, you would have a problem B and a problem A. A is reducible to mapping reducible to B, and if B is decidable, then A is decidable, right? So you could have here also kind of chain in the other direction, right? So from the decidability of B, if you find one problem decidable and that this problem is a mapping reduction from other problems, then all of these problems are also decidable. Okay, that's basically it for this chapter. There is one very important result. The Wright theorem is mentioned in page 219. Basically, if you look at this one, it's very interesting because the way it's built is very arbitrary, and in some sense you look at it, you're like, well, it's just using the regular property to build ATM, but you could use any property of a Turing machine, and that's actually true. Any property of a Turing machine, any specified property of a Turing machine in the language will make this language undecidable. You just cannot characterize properties of Turing machines as a language. That's just not this. I mean, you can do that, but it's undecidable. We show also that LBAs are decidable, and to do that, we just show that there is only so much possible configurations. There is a limited amount of configurations, so that's a very interesting part of the chapter. We use the computation history to show the decidability of some problems. And finally, at the end, we talk about Turing recognizable. So you can use exactly that same argument for recognizable and not recognizable, right? So if B is, based on this, if B is Turing recognizable, then A is Turing recognizable. And same thing, if A is not Turing recognizable, sorry for the mess, B is not Turing recognizable. So you can use the fact that we saw that ATM is not Turing recognizable to show that other problems are not Turing recognizable. For instance, we can show that the problem of actually equivalence of Turing machine, we put it here as undecidable, but it is not correct to leave it as Turing recognizable. Actually, so I should actually take this off and point an arrow outside of the limits, because it is here. It is not Turing recognizable. So we can show that using mapping reducibility, we can show that the problem of equivalence of Turing machines is not Turing recognizable. So it's not just not decidable, it's not Turing recognizable. And we can actually even show, which is a pretty astonishing property of this problem, that it is its complement is not Turing recognizable either. So the equivalence of Turing machines is in itself very, 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 very hard problem, and you can get a sense of why, right? Here we're not just trying to say if a Turing machine is accepting an input or not, but we're trying to say that for one same input, two Turing machines will have exactly the same behavior at all time. So we reach a level of complexity that is beyond what we've seen so far.